Imagine standing on a grassy airfield in the early 1930s. You watch a pilot climb into a cockpit made mostly of wood, wire, and stretched fabric. The engine roars to life with a series of wet coughs and a cloud of blue smoke as the propeller begins to blur into a circle. For everyone watching, this is the absolute height of human achievement. Yet, there is a secret frustration boiling just beneath the surface of the aviation world. These engineers and dreamers knew they were hitting a wall that no amount of extra horsepower could ever climb over. They were reaching the limits of what a propeller could do, and the future of the world was effectively stuck in low gear.
The problem was the propeller itself. As beautiful as those spinning blades were, they were limited by the laws of physics. As an airplane tried to go faster, the tips of the propeller blades would start to move at speeds approaching the sound barrier. When that happened, the air stopped flowing smoothly and started to act like a solid wall. The propeller would vibrate violently, losing its grip on the sky and threatening to shake the entire aircraft to pieces. It did not matter how many cylinders you added to the engine or how much high-octane fuel you burned. At a certain point, the very tool used to move the plane through the sky became its own worst enemy. The world was locked into a speed limit that made crossing an ocean a grueling multi-day endurance test. Passengers on these early flights sat in vibrating cabins, buffeted by storms and low-altitude turbulence, because the engines simply did not have the power to lift them into the thin, calm air of the upper atmosphere.
Then came a radical shift in thinking that sounds almost too simple in hindsight. Instead of using an engine to turn a giant fan on the outside of the plane, what if the engine itself became a giant pipe? In 1937, the world saw the first flickering sparks of a machine that did not rely on a propeller at all. This new invention pulled air into its belly, squeezed it until it was incredibly hot and dense, mixed it with fuel, and set it on fire. The resulting explosion did not turn a crank or move a piston. Instead, it shot out the back with such incredible force that it pushed the entire machine forward. This was the birth of the jet engine. It was a breakthrough that replaced mechanical complexity with raw, focused power. Suddenly, that invisible ceiling in the sky was gone. There was no propeller tip to shatter the air, and the faster the plane went, the more efficiently the engine seemed to breathe. However, building a working engine in a laboratory was only half the battle. To turn this into a way for millions of people to travel, the world had to invent a whole new set of standards. You could no longer build planes out of wood and cloth because the sheer speed and heat would tear them apart. This era saw the rise of advanced aluminum alloys and the development of the swept wing design, which helped planes slide through the air more easily at high speeds. It also required a massive global effort to standardize everything, from the type of fuel used at every airport to the way pilots communicated across borders. The transition was not always smooth. There were early failures, metal fatigue issues that no one had ever seen before, and a steep learning curve for the people maintaining these massive, hot machines. Think about the first people who flew on these machines. They described it as a magical experience. One moment they were on the ground, and the next they were climbing through the clouds at speeds that felt impossible. There was no vibration from a heavy piston engine, and the roar of the propeller was replaced by a high-pitched whistle and a smooth, steady push. For the first time, humans were flying high above the weather, looking down at the storms that used to make air travel so terrifying. But as these planes became more common, the industry realized that speed was not the only thing that mattered. They needed reliability. They needed to know that an engine could run for thousands of hours without a single part failing. This led to a massive shift in manufacturing, where precision became the ultimate goal. Every bolt, every blade in the turbine, and every drop of fuel had to meet a global standard.
The economics of the world began to shift as well. Before the jet engine, air travel was a luxury for the ultra-wealthy or a necessity for the military. But because jet engines were more efficient at high altitudes and could carry much larger loads, the cost per seat began to drop. This was the beginning of the era of mass travel. It was not just about the planes themselves, but the systems that supported them. Huge new airports had to be built, with runways long enough to accommodate these heavy, fast machines. Air traffic control had to be reinvented to handle planes that were closing the distance between cities in minutes rather than hours. The standards that were fought over in the 1940s and 50s became the blueprint for the modern world.
As the technology spread, it created ripple effects that no one could have predicted. It changed the way we perceive the world. Before the jet, international travel was a life-changing event. After the jet, the concept of the international business meeting or the cross-continental vacation became a reality for the middle class. Entire industries, like global tourism and air freight, grew out of nothing. We started eating fruit grown on the other side of the planet and wearing clothes manufactured thousands of miles away because the jet engine made the world smaller. It created a global culture where no two places were more than 24 hours apart. The winners in this new world were the nations and companies that could master the complex art of high-precision engineering. It was no longer enough to be a good mechanic. You had to be a master of metallurgy and thermodynamics. The companies that could build the most reliable and efficient engines became the titans of the 20th century. But there were losers too. The traditional shipping lines that had dominated international travel for centuries saw their passenger numbers plummet. The grand ocean liners that once were the only way to cross the Atlantic were suddenly seen as slow, dusty relics of a bygone age. The world was in a hurry, and the jet engine was the only way to keep up. Why does this still matter to us today? Because we are still living in the world that the jet engine built. When you order something online and it arrives on your doorstep 2 days later from another continent, that is the legacy of the jet. When you visit a relative who lives thousands of miles away, you are using the same basic principles that were perfected in the middle of the 20th century. Even as we look toward a future of electric planes or sustainable fuels, the core idea remains the same. We are a species that refuses to be limited by distance. We are constantly looking for ways to push through the next ceiling, whether that is a physical barrier like the sound barrier or an environmental one like carbon emissions.
The story of the jet engine is a reminder that technical progress is rarely about a single person having a single idea. It is about 1,000 small improvements and a global agreement on how things should work. It is about the standards that keep us safe while we are hurtling through the air at 500 miles per hour. It is about the visionaries who looked at a propeller and saw a dead end, and the workers who learned how to shape metal into blades that could withstand temperatures hotter than their own melting point. It is a story of how a noisy, screaming machine in a laboratory transformed the map of the world into a single, interconnected neighborhood.
And that is how the jet engine and high-speed air travel set the stage for our modern connected world. In the next episode, we are going to take a quick step sideways in the story to look at canals and civil engineering logistics. This missing context will show us how the foundations of moving goods and measuring progress were laid long before we ever took to the skies. If you want to see how these massive systems keep compounding,